Now here we see how we can use the binomial theorem for any general index n, that is when n is say a negative integer or maybe it's a fraction. Now let's see how it is different from the case when n is a natural number. So let's consider, say, if n is a natural number, then we know that previously, as we have seen, if we consider a plus b whole raised to n, that is given by nc0 a raised to n plus nc1 a raised to n minus 1 into b plus so on plus ncn b raised to n. So we are already familiar with this particular expansion. Now to use the expansion when n is not a natural number, we have one restriction, that is we can expand a plus b raised to n in that case when n is negative integer or a fraction, provided we rearrange the given expression into a different form. That is, we have to now consider the expression of the form 1 plus x whole raised to n, where this x is numerically less than 1. That means its absolute value mod of x should be less than 1. So in that case, what do we do is, the expansion is on a very much similar lines, but the only difference is that we don't specifically mention the binomial coefficients in terms of NCR, because n is not a natural number. So the first term is 1 plus, next term is analogous to nc1, which will be n multiplied with power of x. Now here onwards x will start appearing. Now in the next term there was nc2 in the original expansion. So here instead of writing it as nc2, we will just write it as n into n minus 1 whole upon 2 factorial into x square. So you see, if we consider the formula of nc2, that is same as this, but it's just that we cannot write it as nc2 because n is not a natural number. So moving further, if you want to write just one more term, it will be n into n minus 1 into n minus 2 whole upon 3 factorial multiplied with x cube. So that is the way we have to expand this particular expansion, and we will see that this particular expansion will not end because it will have infinitely many terms. That is because if n is a negative integer, if we successively subtract different numbers from it, that is n minus 1, n minus 2, n minus 3 and so on, we will never get 0 because n itself is negative. Okay, so that's why we get infinitely many terms in this particular expansion. Okay, so that is important to remember. Now let's move ahead and see some of the very useful results based on this particular case. That is, we have these 4 very important results, that is 1 plus x raised to minus 1 is equal to 1 minus x plus x square minus x cube plus so on. Instead of 1 plus x, suppose we have 1 minus x, then all the terms on the right hand side will become positive as compared to the previous expansion. Similarly, we have another set of 2 expansions in which the index n is minus 2. So here also we will see that we have a clear pattern, that is we have in the third expansion alternate terms as positive and negative, and in the fourth we have all the terms as positive. Now let us see one important thing, that is what to do if one of the term in the given binomial is not unity. Assuming that n is a negative integer or a fraction, then how can we use the binomial theorem to expand this? Because if you remember, we must have 1 as one of the term in the binomial expansion. So if it is not 1, then how do we do? So for that, what do we do is, let us assume that mod A is numerically less than mod of x. So in that case, somehow we try to arrange A upon x, which will be definitely numerically less than 1. So to arrange that, what we do is, say the given expression is x plus a raised to n, that is equal to, since we want to adjust a by x, what do we do is, we take x common, and here I have 1 plus a by x, and this whole expression raised to n, which gives us x raised to n into 1 plus a by x whole raised to n. And now since we have this term numerically less than 1 and we also have 1 as one of the terms, now we can use the expansion that we have already seen to evaluate this particular expression. Now let's see one example based on the binomial expansion when n is not a natural number. Now here we have to show that root 3 is equal to this particular unending series given on the right hand side. Now here we observe that each term in right hand side has successively increasing numbers. That is, if we look at the numerator, we have 1, 3, 5, that is successively increasing odd numbers, whereas in the denominator, if we see, there are different multiples of 3. So let us see how we can do that. That is, first of all, root 3 is nothing but 3 raised to 1 by 2, isn't it? So we have basically got some power, but inside the bracket we have to adjust the binomial. Now if you say that, well, we can write 3 as 1 plus 2 whole raised to 1 by 2, but the problem is we cannot do the expansion for this because the term other than 1 has to be numerically less than 1, and here 2 is not less than 1. So therefore we cannot split like this, and we must think of some different way to write the required expression. So now here what do we do is, we introduce the negative index. So that means if I take the reciprocal, then I will have to write the negative index. So 3 raised to 1 by 2 is same as 1 by 3 raised to minus 1 by 2. So that now we get a negative index, and now it's easy to rewrite 1 by 3 as 1 minus 2 by 3 raised to minus 1 by 2. And now you see that this minus 2 by 3 is numerically less than 1, and we have also got one term as 1 here. So therefore now we can definitely use the expansion for negative index minus 1 by 2. So that is equal to, we have seen 1 plus x raised to n is 1 plus nx. So here n is nothing but minus 1 by 2 and x is nothing but minus 2 by 3. Alright, so we are just comparing this with 1 plus x whole raised to n. Okay, now the next is n into n minus 1, which is minus half into minus half minus 1 is minus 3 by 2 whole divided by 2 factorial, so that is 2. Alright, multiplied with x square, so that is minus 2 by 3 the whole square. Let's write one more term. Here we have minus half as n minus 1 is minus 3 by 2, and n minus 2 will be minus 5 by 2, and here we have divided by 3 factorial, and then x cube means minus 2 by 3 the whole cube, and so on, since this is an unending expression. So this is equal to, now we have to merely simplify and get the required right hand side. Since there are two negative terms, ultimately it will become plus. On cancelling 2 we will have 1 by 3. So we got the first term, we got the second term. Now in the third term we also see that there are two negative terms and minus 2 by 3 square will be positive. So we will cancel the two 2's and this 2 square will also get cancelled. Also out of 3 square we will have one of the 3 getting cancelled, but we can still write as 1 by 3 into 3 by 6 because that's the way it's given on the RHS. So we won't cancel everything because we want to adjust the RHS exactly like that. And lastly also we can cancel out and finally get the required term, that is 1 by 3 into 3 by 6 into 5 by 9 plus so on. So this is how we get the required RHS.